In this lesson, I will show you how to linearize a graphical relationship. In a previous lesson, I showed you how to take relationships, plot them in Desmos, and determine the type of relationship that was available. Now, in most experiments in our class, this will be fine. But for the AP test, you're going to need to be able to linearize the graph because you will need to be able to determine the values of the graphical values. Those two values that are of importance that you know how to do thus far in your math career are going to be the slope and the y-intercept of the graph. For the other curves, unfortunately, we don't know how to calculate those A values. So we need to do this in order to solve problems in which a computer may not be available. All right, to show you how this works, what we are going to do is we are going to visit a simulation real quick just to show you where the data is coming from. So if I go to this simulation, which is called Forces in Motion Basics from PHET, we're going to run a little quick demonstration on acceleration. So in this experiment, what we are going to try to do is we're going to remove friction and we are going to push on a bunch of different objects that have set masses. And I do want to see the values and I want to measure the acceleration that results. Now, in any good experiment, we know that when we are testing out variables, we must hold any other condition that might affect the data constant. So what we are going to do is apply 500 newtons of force to a bunch of different objects. We have a 50 kilogram object, a 200 kilogram, 40, 80, and 100. So what I'm going to do is I'm just going to simply push, and we see as I'm pushing it, if we look above, we see that there was an acceleration that was there just a moment ago of 10. I'll push that again so you can see it. So again, if I reset the block and I push, we see that we get 10 meters per second squared worth of acceleration. If I continue to do the experiment and I push something heavier, we see that when I push something heavier with the same force, the acceleration now is reading 2.5. It's definitely lower. All right. So far it seems that as I increase the mass, the acceleration seems to be going down. So I would expect if I lessen the mass again, that the acceleration should be a little bit greater than it previously was at 2.5. I push, and I see that indeed it does do that. And I have some values. Now I could continue to do this with all of the different objects if need be. Okay, but I'm not going to do that just to save you time. So what we saw here is that we applied a certain amount of force to a varying mass. Our mass will be our independent variable. And we measured, or our responding or dependent variable was the acceleration that was produced. Now to save some time here, I've already taken this data and I've moved it over to a Google Sheet. According to this, it says this data was obtained by the simulation and we used a constant force. Very important to recognize that this force was constant in every situation. Now we showed in a previous lesson how to get this data over to Desmos. So I'm going to highlight all this. I'm going to hit Control C. That's going to copy it. And now I'm going to move over to Desmos. And right here, I'm going to paste that data by doing Control V. And by looking at this, I do see that I have a graph that appears to be obeying some kind of inverse relationship. As mass is going up, acceleration is going down. All right, so I'm going to try my curve fit rules that we did before. So I'm going to drag this up a little bit, and I'm going to try to see how this is related. So let's see how this variable y1 is related to this a1. I'm sorry, to this y1. So I'm going to try a to the times x1. And I see that that's clearly not right. So it's clearly not proportional, but we were not expecting that. We said it's inverse. And inverse are typically denoted by negative exponents. So I'm going to try something with a negative power. I'm going to try -1 first. And I see that this works really pretty well. We have one stray point that's a little bit off, and that's probably more because of rounding than anything else. But it does appear that my relationship is going to be inversed. So the question is, well, what does this mean that I need to do? Well, what I'm going to do is linearize this. I want to take these points and make them so that they form a nice diagonal line in which I would be able to measure the slope and the y-intercepts for. So here's what I do. I'm going to go back to Desmos. I'm sorry, back to Sheets. And what we said here is that this was an inverse relationship. And an inverse relationship means that the y variable, which in this case was acceleration, was related to the mass, but to the -1 power. So that means that what I am going to need to graph is not the mass and the acceleration, but rather the inverse of the mass. So I'm going to actually type this in as mass. I'm going to use a caret key, meaning an exponent, of the -1. And now what I'm going to do is I'm going to set an equation in which I will take the inverse of these masses. Now the inverse of these masses means that it is really these masses to the -1 power. So I'm going to start by turning this into a calculator by hitting equals. I'm going to use the mass here, and I'm going to do exactly as I did here, caret -1. Now, by the way, this is the same as 1 over mass, but I'm just going to do it based off of the way that I type this. So we're going to put it to the -1 power. And if I do that and I hit enter, I see that it gives me that calculation. And if I drag this down, it will perform the calculations for me. I went one box too far here, so I'll just delete that real quick. All right, so again, if I look, I have the inverse of all the masses. Now, what I would like to do is that we said the acceleration seems to be dependent upon the inverse of the mass. So that means if I plot the inverse of the mass and the acceleration together, I should see a linear relationship. So I'm going to highlight this data. I'm going to hit Control-C, and now I'm moving back over to Desmos. When I move to Desmos, I'm going to put in a new table here. I'm going to do Control-V. Okay, and then we'll notice that now our graph is x1, or I'm sorry, x2 and y2 rather than x1 and y1. I'm going to hide the old graph. All right, I'm going to hide these data points. Now, what I do notice is that this is, because these values are so much smaller, everything appears to be lining up here on the 0 because the numbers in this column, on the x here, if we notice, are much bigger than the values that are over here. So it looks like I need to rescale this. So I'm going to do that right now. I'm going to rescale by clicking on the graph settings. And my x-axis is actually now masked to the -1 power. So I'm going to switch that. And I'm going to actually also make my values make a little bit more sense. I'm going to make this 0. And now my x values appear to go up to about 0.25. So I'm going to go a little past that. I'm going to go to maybe 0.3. I'm sorry, 0.03. Go a little further. And my y-axis is ranging way too far also. So I'm going to switch that. And I'm going to make that go from 0 up to my old maximum number, which I believe I had originally was 15. So I'll just go back to that number. Okay, when I click here, I now see that I have a graph. I'm going to just move it here so I can see it a little bit better. I do see that there is a dependency of the acceleration on mass, but to the -1 power. And this is starting to look like a nice diagonal line for me. So my final thing to do to linearize it is to actually just run the curve fit. So I'm going to do that by saying that, well, y2 seems to be proportional or related to, now I'm going to use m instead of a because you guys are used to this format, the slope-intercept form. Okay, we have mx2 plus b. And what we see here is it does run a nice linear line. Okay, what we do notice here, though, is that this is not proportional. I put this plus b value because this is a y-intercept. I would use this for error analysis because we know it should go through 0, 0, but it doesn't seem to fit there. So for some reason, there was always a value that was just a little bit high all the time, and we would incorporate that into our error analysis. If we take a look, we have some values here. We have slopes given here. We have b's given here. We'll worry about this on a later date, but right now the goal was to show you how to linearize data. So hopefully from this video, you were able to see how to take data, establish a relationship, use that relationship in Google Sheets to create an x variable that would produce a linear fit, bring that data over, and then run the linear fit so that you can obtain the values that are necessary.